Right. So till last class, what we did was I defined what are smooth surfaces, and then actually today what we will do is, you remember always that what we do is. See, whenever we define group, what we have is we give a definition of group, then we do examples, and then actually we define what are the morphism between groups, right? Similarly, when you do topological spaces, we define continuous maps and so on. So similarly, in this case also, what we have is we have a two surfaces are given to us, which are smooth. Then we have to define what is the smooth map between them. So it is kind of a categorical thing. Always, whenever we define some new object in mathematics, what we try to do is we try to give definition of its morphism. So those are actually called the smooth map between surfaces. Okay. So we now actually how to let us see what is the motivation behind this definition. So rather than giving a definition, I'll just first give you how it arrived. So for example, suppose if I have a surface S1 and I have a surface say S2 and I have a continuous map between them. Remember that the surfaces means they are topological spaces first place. So we can always talk about continuous map between two surfaces. So suppose if I have this map F, which is a map from S1 to S2, which is a continuous map, and I want to call this map smooth. So I want to define this notion of smoothness here. Okay. So what is our intuition? So remember, one thing is that continuity, differentiability, and so on, these are local conditions. So we generally try to give this definition point wise. Okay. So suppose if I take a point P and I want to define what is F is smooth at P. Okay. And then we will see how the definition will go through. So what will be your intuition actually, how this smoothness should be defined? What is your guess?
We should take a surface patch around P. Then...
Right. So first place we have to do surface patch around P. That is correct. So very good. So what we have is, so for that, let me define the surface patch sigma. So this is a U1 is given to me and say sigma 1 is there, which is open subset here. Right. Very good. Then what you will do it? Now I have a F of P is also given to me. Here also I need to do something, right? So what you will do here?
Similarly, we will take another surface patch from U2 to sigma U.
Right, that is correct. So we need actually, because see, definition of surfaces, they came from surface patch. So we have to define, define our definition also to be according to surface patch. So let us take this sigma 2 here, which is from U2 to this thing. So this sigma 1, this is a surface patch on S1, and sigma 2 U2, sigma 2 U2, this is a surface patch on S2. So we have these two surface patches. Now now what we will do is we will take a composition of these maps, right? So what is this composition will give me?
Sigma 2 inverse F
sigma 2 inverse composed with F composed with sigma 1. That is correct. So now I got a map from R2 to R2, right? So when I have a map from R2 to R2, I know what is the smoothness, right? What is the smoothness in this when I have a map from U1 to U2, which is inside R2?
All the partial derivatives of order 2 will exist.
Not order 2, we are talking about infinity, right? So we will say that all partial derivative of all order 2 exist and they are continuous. Okay, because smoothness means C infinity. Okay, we are talking about infinitely many times differentiable functions. Okay, right. So but whatever you are saying is correct. So now since whatever we have is from U1 to U2, here actually we know what is the smoothness definition. So I'll say that this is a smooth. Okay, this is precisely a definition of smoothness from S1 to S2. But in this definition, there are some problems are there. What is the problem actually? See, this definition of smoothness, is this only solely depend upon P?
No, depends on the surface patch chosen.
Right, exactly. So this is depends upon surface patch. So suppose if I take another surface patch, then in that case, what will happen is I'll get another I'll get this map will be now changed to another new function, right? And that function will be x2 inverse tilde composed with f composed with sigma 1 tilde at p. So now in this case, what will I wrote a p, but don't take it as a p. Okay, this you have to choose a point u0 v0 here. So it should be u0 v0. Such that f of f1 of u0 v0 is p, but just for abuse of notation, let me write it as a p because it is on the p. Okay, right. So now actually, so here now function is changed, right? So this is a one function, this is another function. So now whenever we define such a kind of thing which is depends upon something other than p and function f, what we have to do is we have to say that these two functions, if this is a smooth, then this is also a smooth, right? I mean, that is what we have to do it. And that will follow because of something which we have done already. What are those things actually, which is called transition functions, right? So what was the transition function? Do you remember? If you have a two surface patch, then what happens? Do you remember, suppose for the same point P, if I have a two surface patch, this one is because of sigma 1, another is because of sigma 1 tilde. Then in that case, what happens is we have this sigma 1 composed with sigma 1 tilde. This map will be from u1 to whatever, actually it will be not exactly from u1. Let me write it as a u1 dash. To u1 dash, these become smooth. So because of that, what will happen is if this map is smooth for one surface patch, this map will also become smooth for another this surface patch as well. So this definition of smoothness is independent of surface patch chosen. Okay, so this is what is precisely a definition of smoothness. So is this clear to you, or shall I just read it again? Actually, whatever I have wrote it here, it is this here. Actually, I just made it more precise. Is this definition okay for all of you? Or at least motivation, then I'll really read whatever I have written there. Pooja, are you there today? Samira, is this definition okay, or shall I explain it again? See, this is very
this
important.
is okay, ma'am.
No, ma'am.
This is okay, right, for all of you?
Oh, okay, ma'am.
Okay, good. Right. So this is what is a precisely definition of smooth maps. So since all of you are comfortable with this, let me just see whether I wrote something extra here. Okay, so here actually, I mean, this is what I gave a definition, and I just made this definition precise by saying here, if you note here, I just made sure that I chose my surface patch to be a smaller so that FO sigma 1 of U1 will be lie inside sigma 2 of U2, okay? And and here, as I told you just now, that if you take another surface patches, then what we have to do is we have to just add these transition maps. You remember these are actually transition map functions. These are transition. And in one of the proposition I wrote to you saying that transition maps, they are smooth. So that will actually give you the required condition. Okay. Okay, and another thing, so now actually what I did is I said that the function is smooth at a point I defined, right? So a function f from S1 to S1 is called smooth if it is called smooth if it is smooth at every point, okay? If f is smooth for every p belongs to S1. Okay, that is a definition. I mean, usual, right? This everybody, all of us are familiar with that definition. Okay, and a smooth map is called diffeomorphism if you have a f inverse is also there. So it is a bijective. So whenever we have a bijective map, what we have is we have a f inverse. This is a defined from S2 to S1. And suppose if this map is also a smooth, then in that case we call f as a diffeomorphism. Okay, right. And whenever we have a diffeomorphism, what happens is, this is actually another thing. See, if you have a Okay, so suppose if you have some patches, so this is again a very simple, I mean, it is immediate thing, but sometimes we use this fact. So suppose if I have a map, smooth map from diffeomorphism from F1 to F2, okay, this is a diffeomorphism. And suppose if I have another sigma 1, this is a patch from some open subset U to S1. Okay, so this is some allowable surface patch. That means this is a smooth patch. Okay, regular and so on. So now suppose if you take a F composed with sigma, this will be a map from U1 to S2 now, right? And F is given to be diffeomorphism. So what is our guess is, this looks like a surface patch only, right? So whether it is, will this be a smooth as well? F is given to be diffeomorphism. I already have a allowable surface patch. Then if I suppose compose with the diffeomorphism, what I'll get it?
A smooth map at least.
Yeah, again I'll get a allowable surface patch also. Okay, you are saying smooth. Okay, so smooth is correct. What about is it going to be also regular? See, what is the allowable means? What you need is, it is a smooth plus what is the another condition is?
The sigma u and sigma v must be linearly independent.
Yeah, they are linearly independent for every point, right? So now suppose if you take a sigma FO sigma u and actually FO sigma, because now this will be, suppose if you call, okay, this okay, so here now actually this is my sigma tilde, right? So I need to show that sigma tilde of u and sigma tilde of v, they are linearly independent, right? And what is given to me is that F is diffeomorphism is given to me, right? So in this case now actually so whenever you have something which is a diffeomorphism, in general what happens actually, conditions you get it, tell me. In general, forget about this surface, I'll go through that proof, but suppose if you have a diffeomorphism from Rn to Rm and that function is F, then what can you say about its Jacobian?
Non-zero.
Yeah, no, see, its determinant is non-zero.
Invertible.
Okay, see one thing, actually Jacobian means I'll consider as a matrix, okay, what you call matrix, okay, and determinant of Jacobian is, we call yeah, one second, I'll just make a straight these terminologies. Okay, sometimes I know that determinant of J itself is called Jacobian, but for us Jacobian is n cross n matrix. Okay, so determinant of Jacobian is non-zero, that means our Jacobian is invertible, right? So our intuition also says that Jacobian of this, for instance, will be some kind of a non-singular thing will give because of chain rule and so on. But of course, don't take it as it is, because we need to do so many things. F is not a function from open subset of Rn to open subset of Rn, so we can't exactly use that. But at least our intuition says that if it is everything goes well, then I know that this has to be something which is a which is something which is a invertible, or and once you have an invertible, a linearly independent vector should go to linearly independent, right? That is what our intuition says, right? We will prove that. Is that fine? First place.
Yes, ma'am.
Okay, so let us see actually what is the proof of this. Okay, so sorry. See, it is one thing is that it is little, I mean, difficult to think that because F is a map as such inside R3 to R3, right? See, F map is defined from the surface S1 to S2, but if you look at actually S1 that is sitting inside R3, right? So when I say that Jacobian, we may start thinking that what is this Jacobian? Is it going to be 3 cross 3 matrix, or it is going to be 2 cross 2 matrix, right? So, but in case of this F, it is going to be 2 cross 2 matrix, because what is happening is we are taking actually, these are our over in the S1, these are the one image of this U and V. These are going to be a form a coordinate system inside S1. So when you write a Jacobian for F, it will be a 2 cross 2 matrix. Is that clear to you? First place, we should actually, that should be little clear because we are going to define derivative also. Is that okay, what I'm saying, or shall I repeat? See, what I'm saying is S1 is sitting inside R3, S2 is sitting inside R3. So it looks like F function is in a map from something from R3 to R3. And whenever you have a such kind of thing, what is your Jacobian matrix for F is 3 cross 3 in general, right?
Yes.
Yes, ma'am.
But our surfaces, they are 2-dimensional. So inside S1, your usual coordinate system XYZ won't work. What actually coordinate system they will have is, because of this parameterization, you will have a U and V, which is, these are U and V, means sigma U and sigma V, okay? And here actually U prime, V prime, these are going to be their coordinate systems, okay? So because of that, if I want to write a Jacobian of F, which whatever that meaning is, it is going to be 2 cross 2, no, 2 cross 2, not a 3 cross 3. Okay, is that fine? I did not define Jacobian so far. We will come to that at the end of our class. Okay, but is this at least okay with you? Actually, whatever I'm trying to kind of convince it to you. Okay, so but in this proof we are not going to use that Jacobian and all that kind of thing. What we are going to do is we want to show that this new thing, which is a sigma 2 composed with sigma 2, which is F composed with sigma 1, this is going to be allowable surface patch on S2. Okay, so for this actually what we are going to do is sorry, FO sigma 1, I need to show it to be, it is a smooth, that is clear, because F is also smooth, sigma 1 is smooth, so this is smooth. So and anyway, if I want to tell anything, what we have to do is we have to always start with taking a allowable or smooth surface patch. So let us take sigma 2 to be a smooth surface patch, okay? So then what happens is, if I take a sigma 2 inverse O F O sigma 1, can you see this part? This part. So this is going to be a map from where to where, U1 to, because this is sigma 1 F composed with sigma 2 inverse. This is a map from U1 to U2. And what is the definition of smoothness for F is precisely this map is a smooth, right? That is precisely our definition, right? So let us take F to be sigma 2 inverse O FO sigma 1. Okay, I'm just denoting this by F. And now what can you say about this capital F? This is a map from U1, which is an open subset of R2 to open subset of R2. Now here we know what is the diffeomorphism is, right? It is a usual diffeomorphism. So now our question is whether this is a diffeomorphism. So in order to show that this is a diffeomorphism, what we have to do is we have to find its inverse, which is also smooth, right? So if you take this map, sigma 1 composed with F inverse O sigma 2, because F is diffeomorphism, I can take F inverse here. So sigma 1 O F inverse of sigma 2, this is going to be also smooth because F inverse is also smooth, okay? And this is clearly inverse of capital F. So because of that, what we proved so far is F is a diffeomorphism. Is this clear to you? Why capital F is diffeomorphism?
Yes, ma'am.
Okay, so now capital F is a diffeomorphism from where to where, U1 to U2. Okay, now if you remember in last class, what we have done is if you have suppose surface patch. So here actually what we have is we have this sigma 2. This is a surface patch from U2 to S2. And what we have said last time is, suppose if phi is a diffeomorphism from U1 to U2, then sigma 2, so both of them are inside R2. And this is a diffeomorphism inside R2. Then what happens is sigma 2 composed with phi. This is a map from U1 to S2. This is also allowable surface patch. Do you remember this? We did it last time. See, in this case, what will happen is this will be clear because phi is a diffeomorphism, and you know that Jacobian of phi, this is invertible, right? See here, what happens is why this is very clear that this is allowable patch. Can you tell me? Smoothness will come directly, right? Sigma 2 composed with phi. This is a smooth because phi is also smooth. Sigma 2 is also smooth. And why actually this sigma 2 O phi is yeah, with respect to say whatever u and v, why they are going to be a regular? I mean, why they are going to be linearly independent? See, given to me that sigma 2 is linearly independent, phi is diffeomorphism, then can you say that these are linearly independent? Do you know chain rule, right? So what will be sigma u? Can you tell me? It will be Jacobian of phi times actually sigma u, right? I mean, whatever sigma u tilde or those kind of things, right? So if this is actually a non-singular matrix, then certainly when you multiply to two of them which are linearly independent vector, they will give you again linearly independent vectors, right? Do you remember this? We did it last time.
Yes, ma'am.
Right. So because of that, this is actually a allowable surface. And once this is a allowable surface, what is going to happen is, so in general, this is a statement. So now what you do is you take this sigma 2 OF. What is sigma 2 OF? This is going to be allowable patch because of our just now whatever we discussed. And but what is the sigma 2 OF is? F is given by sigma 2 inverse composed with F, right? This is a definition of my capital F. So if I substitute here, I'll get a F for sigma 1, okay? So because of that, this is going to be a smooth patch. That is what we want to prove. Okay, so whenever you have a diffeomorphism, what we can do is we can transfer our surface smooth patches from one surface to the another surface, which is actually a kind of a good thing to have it. Okay. And then actually, but many times what happens is our functions are not a diffeomorphism. That is little very strong condition of a diffeomorphism. But sometimes, but remember that differentiability, continuity, all of these are local properties. So sometimes even local diffeomorphism also is something which is sufficient to us. Okay. So what is a local diffeomorphism is? If for every point S, you can find an open neighborhood where your function is diffeomorphism. Okay. So it may not be a globally diffeomorphism, but locally it is. That means for every point P, you should able to find a open subset which will give you a diffeomorphism. That is the definition of local diffeomorphism. An example for this is very simple example is there. So what we are going to do is, suppose if you have this S1, this what is this surface S1 is? This is a YZ plane, right? So what is the YZ plane means? Our x coordinate is going to be 0. So I have this S1 which is 0 YZ, y comma z belongs to R, and another is cylinder. So what we are trying to do is we are trying to wrap this entire plane to this cylinder. Okay. So is this function is diffeomorphism? Is this a function which is bijection? What we are doing is we are taking this plane and we are wrapping around the cylinder. Is this going to be a bijection?
It's not injective because we are wrapping it again and again.
Right, exactly. So the injectivity will certainly lose. In fact,
Subjectivity will be there, I think.
yeah, subjectivity will be there.
Injectivity is lost.
Injectivity, in fact, for every point, you will have infinitely many pre-images will be there, right? Because you can take everything, you just add 2 pi to it and you will get it. So this is certainly not a diffeomorphism, but we already know that this is locally at least diffeomorphism. We can prove it, right? Because so how to prove actually this is locally diffeomorphism? So what is the local
consider
diffeomorphism?
only one round, like just one round, 2 pi.
Right. So we have to take actually just a 1 round. That is correct, Devi. So what we are doing is, suppose if I take it from 0 to 2 pi, okay? But 1 round also we cannot take a completely because then continuity will be lost, right? Because if you take actually this point at this point, they are coming together in this, but they are far apart into this this plane, right? So what we are going to do is we will take actually our range to be 0 to 2 pi and z, and then what will be our map is, and you sent so anyway map is there. So now f restricted to u1 to our cylinder, and anyway that map is there, so it is y comma z 0 that we are sending it to cos y, sin y and z, right? So now actually, is this a diffeomorphism? Is this a bijection first place? Certainly not a bijection, right? What is missing here? Yeah, that line, na, which is that line will be actually when x coordinate is what 0 is missing. No, x coordinate y, sorry, 1 0 comma z. This entire line will be missing, but that line is a closed right line. See, this L is a closed subset, so S minus L will be open, right? See, what is our local diffeomorphism means? You should restrict our map and it should go from open subset to another open subset. So this is a open inside U1. Is this open inside cylinder? S minus L, is it open?
Yes.
Right, because L is closed, right? So in fact, what you can do is you just take a entire R3 minus this line L. This is open, right? See, from R3, I can remove the line L. This is open because L is closed. And now if I take intersection with S, what I'll get it, open subset of S, right? So because of that, this is open. So here I need to check that, is this map diffeomorphism? So is this map diffeomorphism? See, this we have checked it, right? This is almost like a surface patch, right? You remember? These are cylindrical coordinates only, right? Almost. In our cylindrical coordinate, what we did is we took actually theta cross t. So here actually theta is like our y and t is like our z, right? So this is clearly a diffeomorphism here. But now in this case, what is happening is, if I take like this, my plane won't be the entire, right? So because what we want is for every p, I need to find diffeomorphism, local diffeomorphism. So now in this, what are the points which are missing actually from this plane? From this plane, what are the points which are missing if I take this diffeomorphism?
Multiple pi.
Okay. I just defined from 0 to 2 pi, right? But can you define for all the patches? See, I wrote it as a U1, but you can also take it from same thing from 2 pi less than y less than 4 pi, comma z. I'll come back to you. Actually, just one sec. I did not say, I just wrote a U1, but this is also true for 2 pi less than y less than 4 pi z, right? Is this okay, Priyanka, Pooja and all of you?
Yes, ma'am.
So because of this, what will happen is plane only things which are missing from here are going to be, as he said, 0, 2 pi, and then what are those 4 pi and those kind of thing. So now suppose if I want to, so who is that person who is answering? Actually, Sumit, is it?
Swarup.
Swarup, okay. Swarup, you are from SNU only, right? Swarup?
No, ma'am.
You are from which place?
In North Bengal, University of North Bengal.
Okay. Yeah, which is you are correct, Swarup. So the things which are missing is the multiple of 2 pi. Okay. So now how to avoid the, so but now I need to consider those points also. So in that case, what you will do is, how you will avoid this, how you will now consider the another open subset so that I can incorporate, I can consider those 0 2 pi also inside my this some diffeomorphism. Can you define for those points?
We will take from another patch from minus pi to pi.
That is correct, right? So what we can do is we can just take it from minus pi to pi, and then you take the same map. You don't need to change your map. Only thing is that this line L will be converted to which line? If I take like this, what will be this line? See, if I take a minus pi to pi, what are the points which are missing from cylinder?
Then it will be the line -1, right?
Right,
-1,
-1 0
0.
z, right. So and then the same thing will work. Okay, so this is actually that is what I wrote it here. I'll share the notes so that you can see it. Okay, so this proves that this map, though this is not a diffeomorphism, it is local diffeomorphism, and many times now we actually manage with the local diffeomorphisms. Okay, that is enough for us. So this is about the smooth map between surfaces. Okay, so this is something which is actually are there anybody who knows categories or something like that, or you people are not
Yes, ma'am.
introduced? Right. So, but what about others? I don't want to use these words to scare. Priyanka knows. What about Mahinshi Singla and Kartikeya?
Yes, ma'am. I have done that categories.
Yeah.
Basics.
A
Yeah.
basic only I'm talking about. So what I want to just say is that suppose if you take now this category of smooth manifold. So what is this actually? Object of these categories are smooth surfaces. Okay. So you take a collection of all smooth surfaces. And then actually we have to, so whenever you have a category like that, what you have to define is you have to define a map between them, right? Homomorphism from in these categories. So what are these maps are going to be? They are smooth in the above sense, whatever the sense which we have defined. And then actually this C will become category. Okay. So now we are going to work in this particular category. So suppose if I say surfaces, that means we are talking about smooth surfaces. If I am talking about some map between S1 to S2, whether I say or not say, I'm talking about smooth map. Okay. Whenever I'm talking about say patches, always remember that I'm talking about smooth patches. Okay. I want to say you one more thing also. See, the surface patch is there, na? The smooth surface patch. Suppose if it is from U, which is, let me call this as a UV frame, and to surface S1, some surface S. So what can you say about this map sigma? Is this, can you consider U as a surface? Is U is a surface in our sense?
Yes.
Right, that is correct, right? Because what we can do is we can always actually embed this R2 inside R3, right? Just to put some extra variable if you want W. And then actually this is a map from surface to another surface, right? And then actually, what can you say about this map sigma? Is it a smooth?
Yes.
It is a smooth. Is it a diffeomorphism from actually, don't take it from S, then you take it from sigma U. So sigma map from U to sigma U. Is this going to be diffeomorphism?
Yes, ma'am.
Right. So the actually now these things need some proof, but let us assume this. Okay. I don't want to, I mean, you have to take some surface patches and so on. It is immediate, but the thing is that you have to write little longer. Okay. So remember that this sigma, this is a smooth map between two surfaces. If you consider this R2 to be embedded inside R3, and it is going to be in fact diffeomorphism more than that. Okay. It is not just a smooth map, it is also a diffeomorphism. We see, so far we did not take this. You remember that whenever we defined it, we took it as what actually sigma composed with sigma inverse. These transition functions were diffeomorphism, right? You remember this actually, because we were, that time we were not considering U to be actually a surface. Do you understand this, or shall I should have not said this. Okay, maybe let us see actually whenever it comes. Okay, I mean this is going to be a diffeomorphism, but I don't know whether I'm going to use it or not. All these things that he discussed in the section 5.6. Okay, but so far remember that this is also a smooth map. Okay, until this is fine, and it is also a diffeomorphism. But let us, for a time being, let us keep it aside, because again then I had to say something more than that. Okay. So, so we are going to now deal with only in the smooth category. Okay. So that is what I want to say. So this is something which is important things when we talk about surfaces. And one more thing I want to mention here is, remember that all these things, whatever I'm telling this only holds for the way we define surfaces. Okay, how we define surfaces, they are embedded inside R3. Okay, this is not in general true, because some of you already know manifold theory. So I'm telling you that this, whatever this part which I wrote it, this is in general not at all true if it is in general manifold. Okay, we are not talking about that, because we have to kind of embed inside certain things. Okay, so don't take this for a general manifold. This is only for the way we defined our smooth surfaces. How our smooth surfaces are defined, they are embedded inside R3. Okay, right. So now actually another important thing about any kind of a surface is, surface means any kind of a geometric object, is to define tangent, right? You must have defined tangent for curves. You defined so far tangents for curve.
Yes.
Right. So now actually what we have to define, do is, we want to define actually a tangents for the surfaces. But tangent for surfaces, they just comes from tangent for the curves only. Okay. But what we do is, when you take a curve, tangent vectors are just a multiple of one single tangent vector. But here actually what will happen is, we will have many tangents vectors will be there. So we have to define this notion. Okay. Right. Okay, so let us now define this tangent plane for the surface. So see, remember that when you have a curve, this is a one-dimensional object, right? Right. So whenever then you have a tangent, that is also going to be something. See, it is a tangent vector, right? You can just multiply it. So you can consider it as a line rather than, I mean, okay. Right, sorry. So when you have a curve, what we have is, we have actually a tangent here. But suppose if you have a surface, suppose if I have something like a sphere, then in that case, what will happen is, you have actually many things which are going from the point, right? Many curves. So what we are going to do is, we are going to actually collect all the curves and all the tangents to these curves, right? So what we will do is, you will take a point, we will pass the curve through it on the surface. Okay, so this curve will be inside the surface S, and then what we are going to do is, we are going to take a tangent to that curve, and we will put it into one space which is called TPS. We will denote it by, and this will be called tangent space. Okay. So this is a one. Then what I'll do is, I'll do another curve. I'll take it. I'll look at its tangent. I'll add that also inside this. So that is how our tangent space is created. Okay. So what we do is, so let me define it. So let S be a smooth surface, and P belongs to S is a point. Then a tangent vector to a surface S at a point P is a tangent vector at P to of a smooth curve passing through P. Okay, so what we will do is, we are looking at now tangent plane at a point P. We will just look at how if there is a smooth curve which passes through that point, and then we will write down its what we will do is, we will write down its tangent. But now actually in this case, I need to say certain things. Do you know what are smooth curves inside R3? See, we have to actually say, what do you mean by smooth curve inside the surface S?
It is a smooth map from the open interval to S.
Right, but then actually we have to we did not define it so far, right? Sorry. Okay, so what is your meaning actually? Can you just tell me? So how you want to take it? This I just define a smooth map from some open what you call open surface to open surface. That's what I did, right? So I have to say what is a smooth curve is. Okay, it is. I'm not define it separately, but what is your intuition? Which curve will be smooth? You will say. See, as such, I did not define smooth curve. Do you agree with that? Did I define so far smooth curve?
No, ma'am.
Right. So what should be a definition of smooth curve?
Ma'am, we can consider the surface to be embedded in R3. So we'll say a curve is
No,
smooth.
but
We'll consider.
no, but see, minus epsilon to epsilon, now how you will embed it and then how you will define a map from the whole of gamma. See, we define it from one surface to another surface. Now, I did not define it from the one-dimensional object to two surface, right? But you can just go back to our previous thing, right? The patches. We always go to surface patches. So, in terms of surface patches, can you tell me what should be a smooth definition? Okay, this part now, I'll just give me 1 sec, okay. Okay, see, what is the curve is first place, let me go to a curve. What is a curve means, can you tell me what is the curve? Curve passing through P, what should be a definition?
A smooth map from the interval to
No,
S.
smooth we did not define it. So you consider as a continuous. Okay. With smoothness we did not define for the surfaces so far. So take a continuous map. Continuous it is defined. Okay. Because it is topological space, right? It is having a subspace topology. So it is a continuous map gamma from minus epsilon to epsilon. Let us take it. Okay. To S, such that gamma of 0 is equal to P. See, we can always shift our whatever. Is that okay? Is this a curve? All of you agree?
Yes, ma'am.
Okay, so this is my gamma of gamma, okay? And this is a gamma of 0. So this is actually a curve. Now, if I want to say smooth curve, what I'll do is you take a surface patch. Okay, so take a surface patch sigma from, see, this is, we are talking about a curve at a point P. So we can always shrink our minus epsilon and epsilon so that I can give a surface patch sigma, for instance, from U to sigma of U here, such that gamma of this minus epsilon to epsilon, this lies within our surface patch. Okay. Suppose if it is a big, what you do is you just take an inverse image and make it smaller. Is that okay? So can I assume this? Is all of you are okay with assuming that this image of gamma lies inside surface patch sigma U?
Yes, ma'am.
Yes, ma'am.
Okay, right. So now actually, so this is a surface patch is given to me, gamma is given to me. Now actually what we can do is, since, so this curve, what I can do is now, since sigma inverse is there, what I can do is I can take a sigma inverse, compose, what I can do is, I can take sigma inverse compose with gamma. This is a map from minus epsilon to U. So which is contained inside R2 now. Okay. So here, can I take call this as a smooth? I mean, can I say that this should be a smooth? See here, now we know what is the smooth curve inside R2, right? All of you know what is definition of smooth curve inside R2. Because this will be like a ut comma vt, and then all these, both of these ut and vt, if their derivative exists for infinitely many times, then we will say that this curve is smooth. So this is our definition of smooth curve. So what is the smooth curve is? For given a surface patch, you should have this to be a smooth. Is that okay? So such a kind of curves we are going to call as the smooth curves. Okay.
Okay, ma'am. Okay.
And now what you do is you look at gamma dot of t, and then actually whatever, so that will be a vector, and that vector we will put it into tp of s. Okay, so this is our notation for tangent space. So now actually I'll tell you how this gamma dot of t will look like, because what is going to happen here is, look at here actually how this gamma t will look like. So gamma dot of t, that will be a map like xt, pi t, and ZT, right? Because all of them are where actually they are inside R3 only, right? These are belongs to S, which is contained inside R3. Okay. And then if you take this tuple, that we call this as a beta, and what will be beta of T, how it will look like? It will look like UT comma VT, right? I'm just writing it. Okay. So beta, this is a map from minus omega to minus epsilon to U. I'm denoting it by UT VT. Okay. Then what I'll have is I'll have a sigma composed with beta of T. Oh, sorry, this is not a dot. Okay. So this will be what actually? This is going to be a X of UT VT, Y of UT VT, and this is Z of UT VT. Okay, and this is equal to our this xt, yt, and zt. Okay, so now actually, if I want to find gamma dot of t, what will be your gamma dot of t? Can you tell me in terms of this? See, this is just x dot of t, y dot of t, and z dot of t. But if I use a chain rule, what will be this? This part, this side is. See, this is actually our LHS. Can you tell me what is the RHS differentiation is? See, what is the differentiation of this with respect to T, sigma composed with beta of T?
Del X, del U, U
Okay,
dot
yeah, that is
plus
correct actually. So
del-
shall I write
del
XU
V.
just for XU, then YU, ZU? Is it okay? That's what you are saying?
Okay.
I mean, I'm not writing that del U. Is this notation okay now? What is the XU means? Actually, I'm just saying del X by del U, okay?
Oh, okay, ma'am.
Okay, this is notation wise, okay? Then here what you will get it? X of V, Y of V, and Z of V, right? And this, and then what you will get it here? So this is actually 3 cross 1, right? And here this is what 3 cross 2. What you will get it
Yes.
here actually?
U prime,
U dot
U prime, V prime.
U dot T, V dot T. Actually, what is your notation actually? I don't know. That book notation was dot. So I wrote it here as a dot. What is your notation in general you are using it?
Yes, with respect to T, we are using dot.
Hana, right. So here also U is with respect to T, right? So we can use a dot, right? So this is a 2 cross 1, right? And what is this actually? This is our that sigma U, remember? And this is our sigma V. This was our notation. Is that okay? Do you remember this was our sigma U and sigma V notation, right? Which we defined it in the previous class. What was that regularity
or
condition was?
Jacobian.
Sigma U, sigma V is
No.
linearly independent or not equal to 0.
Yeah, right. This right. That is
This
correct.
sigma U cross sigma V not equal to
Ah.
0.
Right. So now actually, can you say me, so can you write down this actually? So this is now I'm writing in terms of say vector. So what you will get it actually, can you tell me what is this product is RHS? See, this is what it is XU plus, see, this is what it is. This is this X dot T, Y dot T and Z dot T. What is this? This is equal to XU times U dot of T, right? Plus XV times
V
V
dot
dot
T.
of T and so on, right? Can you write down this? What will be this? This is YU U dot of T.
U dot T plus YV V dot of T, ZU U dot of T plus ZU U dot V dot of T. ZV V
Right.
dot of T.
So now suppose if I want to write them in terms of sigma U and sigma V, what this is a U dot of T. This is a scalar, right? This is a scalar times sigma U, right? This is a vector. See, this gamma dot of T, this is vector. This is also a vector. See, tangent means this is a tangent vector, right? I mean, that is how we are defining it, tangent vector. So I got a scalar times sigma U plus V dot of T times sigma of V, right? So here also this is scalar and this is a vector. So what you got it just now is This tangent vector, that is a linear combination of these two vectors. Do you agree with me?
Yes, ma'am.
Is this okay for all of you? This vector,
Yeah.
tangent vector, I wrote it as a linear combination of two vectors. And remember that the sigma u and sigma v, they are not dependent upon gamma, right? See, the sigma u and sigma v, they are not dependent upon gamma. See, actually what we want to say is actually when t is equal to 0 only, we have to take it. Okay, this is sigma u of u dot v naught, it will be. See, because we are looking at a tangent at a point P, right? So let me just write here, then I'll explain you what is this. See, we know that gamma of 0 is P, right? And we are taking u naught and v naught are such that inside u, which are sigma of this u naught v naught is equal to P. Okay, so essentially this gamma naught of 0 is this one, and these are independent of gamma. Okay, but these will be dependent upon your gamma. Okay, and these are independent of gamma. So what we showed just now is any tangent vector is a linear combination of these two tangents, and what we know about these two tangents are they are linearly independent, right? Do you know that? Do you remember this? These are linearly independent for surfaces.
Yes, ma'am.
Independent. So now our guess is that whenever, I mean, these tangent vectors, they are linear combination of linearly independent vectors. So it is possible that TP of S, this is going to be a two-dimensional vector space. This is our guess. See, we did not prove it so far. Okay, what we showed is that any tangent vector is a linear combination of this. Suppose if I want to say that this is a two-dimensional vector space generated by, say, these two vectors, what I have to prove it? Suppose if I want to say that it is generated by these two vectors, what you will do?
Every tangent vector is a linear combination of sigma u and sigma v.
That we showed here, Pooja, that is done. I want to say now reverse way. Any linear combination of the sigma u and sigma v, that is a tangent vector if I show,
Okay.
then they are equal, right? And
Yes.
that is also, okay, so that is very simple. What you can do is, suppose if I take any linear combination, suppose if I take a times sigma u plus say b times sigma v of u naught v naught, what I have to do is I have to just find an appropriate curve. And what is that curve will be? So what you do is these two, this curve is you take it via these timings now, they are just giving me tension. Okay, so see what we have so far, we have our sigma here, right, which is a surface patch which is going inside S. And suppose if I have some curve gamma, which is let me call it as a beta, which goes inside U. Okay, so for example T, I'm sending it as a what I'm sending it as a, see, u naught, we know that this u naught comma v naught, this is an element inside U, that we know, right? Because what we have is sigma of u naught v naught. What is this? This is P. So this element is here. So suppose if I send this T to u naught plus at comma v naught plus bt. Is this now actually if I take a sigma composed with beta, this is a map from minus epsilon to S. Is this a smooth curve? See, what is this? I'm sending it to, this is a linear, right? U naught plus at, v naught plus bt. Is this a smooth? Beta is smooth? Is
Yes.
beta
Yes,
smooth?
beta
Yes, ma'am.
is smooth, alpha is
And
smooth,
sigma,
sigma is smooth.
so yeah, their composition is going to, or sigma is essentially a surface patch. So sigma composed with beta by definition is going to be a smooth curve, right? Because what was the definition of smooth curve is? Composed with sigma inverse has to be smooth. And if you do that, beta is there and beta is a smooth. Okay, so because of that, this is actually smooth curve. And now what is actually its what is the u dot what is that what is the so this is gamma. So what is here actually u dot of t, u dot of 0? See, this is our curve, right? What is the ut here? That is the u naught plus at. So what is the u dot of 0?
U naught comma V naught.
U naught of 0, I'm just asking. 1.
A comma B.
No, Ray, it is u naught, Ray. U naught means just a
Oh.
first. Ut is a u naught plus at. This is inside R to R. See, U is a map from R to R. I'm taking R to whatever U, but it is a one dimension only. Na? R is going. Is this okay? U dot of 0 is A because.
Yes, ma'am. Yes,
And
ma'am.
what is the V dot of 0 is?
B.
P, right? So now if you substitute in our earlier formula, what is this actually? What will be a gamma dot of 0 is? If you substitute here, you will get A times sigma U.
A sigma U plus B sigma V.
See, and here at up U naught V naught is precisely this, right? So, so what I did is I started with some linear combination of this. I started with a W, which is a linear combination of sigma U and sigma V, and I showed that it is also a tangent to this particular curve. That means I showed that TPS is precisely a vector space inside R3 generated by the sigma U and sigma V. Is that okay with you?
Yes, ma'am.
See, okay, actually just I wrote it down very clearly over here. So just to go through these notes, okay, I'll give immediately to you. So that that's what essentially in these entire notes we did it, okay. So, and actually here now one example we should see, otherwise now it is very difficult to visualize it. So let us see example of a sphere. Let me just take here another 2-3 minutes, okay. So in sphere, what is, we have seen lot of different surface patches, right? So what is one of the surface patches? This, right? So this spherical coordinate. What is this surface patches? Is this okay for you? Do you remember this?
Yes, ma'am.
Theta comma phi goes to this. So let us try to find out what is the TP of the sphere. Okay. So how you will calculate TP of sphere is, we have to first calculate. So here what are our parameters are theta and phi, right? Theta is one parameter, another parameter is phi. So what I have to do is I have to find what is d theta is and d phi is. Is that okay?
Yes, ma'am.
So what is the d theta is? See, this is our function, right? Our function is this. So what is d theta is? Is this okay for you, d theta?
Minus sin theta. Yeah.
Okay. And what is the d phi is? This. So this is actually, we are doing a partial derivative with respect to theta here. And we are doing partial derivative with respect to phi here. Right? So now actually what I want to say is that, so TPS is going to be R d theta plus R times d sigma phi. Okay, this is by just now whatever we proved it. Are you convinced by this?
Yes, ma'am.
Okay, but do you remember actually what are the tangent space for sphere? Priyanka, do you remember tangent space for sphere, how it looks like? Or Pooja, do you know what is the tangent?
A plane.
Yeah, what is that plane? Can you tell me actually in general when we define it, how we do it?
we need a
Do you
normal
remember?
vector from.
No, normal vector, it's fine, right? Just forget it. But see, that is what is different. But see, remember always that for sphere, what is a tangent space is all those vectors inside R3 which are perpendicular to it. Do you remember this actually? See, if you remember one thing is that for sphere, what is a TP? Because this, even in algebra also we use it, even in geometry we use the same thing, okay? tangent space plane for sphere is very important. Even if you are doing commutative algebra, even if you are doing abstract algebra, you are doing algebraic geometry, you are doing differential geometry. Okay, in all the places, tangent space of sphere comes into picture. Okay, and remember that what is the tangent space of sphere is all those vectors which are perpendicular to that point P. Okay, that is how this tangent space is space comes. So now let us verify that if I take a point from this sigma theta sigma phi, it is tangent to my point P. Okay, so how you will check that? Even if you show that sigma theta and sigma phi, they are tangent to my original point, then also I'll be done, right? Because then every linear combination will also give the same thing. And how you check two vectors are tangent to each other? If I want to check
Dot
two
product
vectors,
is equal to 0.
right. So what I have checked here is d theta dot p, that will correctly come to be 0, and d phi dot p is also comes to be 0. Okay. So don't forget this. Remember that whenever tangent space of sphere, always remember that this is something which is a plane which is perpendicular to that point. Okay. See, another two things which I was supposed to say was, let me just quickly, in 1 minute, I'll just say, suppose this is very important thing is that you read this thing. Okay, so I'll just tell you what I have written here. So suppose if I have a surface and suppose if P point is given to me. Okay, and for this point, whatever so far I define my tangent space, that is solely depend upon surface patch, right? I fix my surface patch and then I define my tangent. Is that correct?
Yes.
So now suppose I give you another surface patch is given to me. Then in that case, what will happen is, so here actually, but see, TP of S, by definition, it is independent of surface patch. Do you agree with this? What was our definition was take a curve and take a tangent to it, right? So it is nothing to do with surfaces. Do you agree with me?
Yes, ma'am.
But what proposition I did was I told you that if I take a surface patch, sigma u and sigma v, they are going to actually generate my TP of S. So when I gave that proposition, in that case only it started depending upon surface patch. So now suppose if I have another surface patch around P, what will happen is suppose here sigma tilde, it is depends upon say u tilde and v tilde. Then I'll have actually now another set of vectors which will also generate TPS, right? Do you agree with this? If I choose another surface, then what will happen is if I look at this sigma tilde u tilde and sigma tilde v tilde, they will generate my same tangent space.
Yes, ma'am.
Is that okay? Right. And whenever, suppose if you have a tangent vector space which is consisting of 2 points, two-dimensional vector space, and you have a two bases, then what can you say about those? So what is the relation between these two bases?
One can be written as a linear combination of like sigma tilde can be written as some linear combination of sigma u and sigma v.
See that, but what is
Sigma
that?
tilde u tilde is on the plane, and sigma tilde v tilde is sigma tilde u tilde and sigma tilde v tilde are on the plane generated by sigma u sigma v.
Yes, that is correct. But what I'm saying is, suppose if you have a same vector space and if you have a two different bases for it, how you write actually those two bases? Not linear. I mean, it is not only linear combination. No? There is a what you call whenever you have a two bases. What is that matrix which you write it?
A change of basis.
Exactly, you write a change of basis matrix, right? And what property of that change of basis matrix happens?
It's invertible.
It is invertible, right? So precisely sigma u, sigma v, and sigma tilde v tilde. In between them also there should be some matrix, and which is an invertible matrix, right? And that matrix precisely comes out to be a Jacobian. See, when you have a two surface patches, what happens is we already have seen that sigma tilde inverse composed with say sigma. This will be actually will give me some Jacobian, right? I mean, this is a smooth map that is by definition, that is one of that proposition is there. So if you look at a Jacobian of that, that will be 2 cross 2 matrix, which is an invertible matrix, right? Do you agree with me on this? Jacobian of transition maps, that is going to be invertible matrix. And actually, if you want to write a matrix of this transformation, that will be precisely comes to the Jacobian matrix. So that is what precisely I wrote it here. So you can see the details with those notes. Okay. So only two things now remaining for this our what is that from that fourth chapter is one is orientability and another is differentiable map. So those things now I'll just quickly we will do it in some, I mean we will do it. Okay, I'll stop now because you must be having your tutorial. So I'll give you a lecture notes. Please go through the lecture notes because many in today's class many details. What I did is I did not proved it. So just go and see the proofs over there. Okay. So I'll stop now. If you have some doubts, you can ask me.